Thank you for the introduction. Good afternoon, everyone. My name is Wang from City News Hong Kong. Uh, I'm here today presenting on behalf of my colleagues from City News Hong Kong who unfortunately couldn't attend ISCA due to visa issues. I'm excited to present the ArtMem adaptive migration in reinforcement learning enabled tiered memory. Let me start by providing some background on why this problem matters. And DRAM-only systems experience significant drawbacks of high cost and insufficient capacity due to increased memory from applications like machine learning, graph processing, in-memory database, and so on. Memory now account for approximately 40% of server cost in data centers. Tiered memory systems offers a combining solution by combining faster DRAM with slower but cheaper memory technologies like persistent memory and CXL attached memory technologies. The key change is that to maximize performance, we need to place frequently accessed hot data into fast memory tier through careful page migration policies. And poor migration can severely impact performance, as applications might end up accessing the slower memory for critical data. Let me show you how existing systems approach this challenge. As you can see in this table, current tiered memory systems usually use different combinations of frequency and recency metrics to make migration decisions. For example, ArtMem, sorry. For example, you might use recency but not frequency, rely on static parameter settings. And MemTs use both frequency and recency but with heuristic parameter settings. The key limitation here is all these systems use static or simple heuristic approaches to set critical parameters like the hotness threshold for frequency and the migration count. And the static nature of these approaches means they can't adapt to diverse and dynamic workloads. Dynamic memory access patterns we see in real applications. To demonstrate this problem clearly, we created 4 synthetic workloads that represent the different memory access patterns. And these patterns are commonly seen in real applications. S1 shows high access locality, S2 has temporal access, S3 has broader hot regions, and S4 is hot region is larger than DRAM capacity. We run these workloads against 7 SOTA tiered memory system. The result show execution time normalized to a baseline, which lower is better. The results are quite revealing. Each system performs well on some memory access pattern, but poorly on others. For example, adhering excels on S1 and MemTs works better for S1, S3, S4, but it struggles with S2. Multi-clock fails on S4. This leads to our first key observation. Existing methods may perform well on certain workloads, but poorly on others, and no single existing approach works well across all access patterns. We discovered a strong correlation between system performance and the percentage of memory access that is in the fast memory tier. And these correlations plot show Pearson coefficient larger than 0.8 across all these different systems. This gives us a second observation. A low access ratio in the fast memory tier indicates that current page migration mechanism is ineffective under such conditions. And this insight is straightforward, but it's crucial because it provides a real-time metric for us to evaluate how our tiered memory system is performing and can guide us to make some adaptive decisions. And we also found that manually adjusting these migration parameters for specific workloads can also dramatically improve performance. For example, when we manually tune the Memphis hotness threshold for these two workloads shown here, and we reduce migration volume and the execution time gradually significantly. And this leads to our third observation. The memory migration parameters should be tuned dynamically for different workload patterns. And however, manually tune these parameters for every workload is clearly impractical, if not possible, in real systems. This brings us to the core challenge. How do we automatically adapt migration these migration parameters to diverse and dynamic workloads, while predictive models trained on historical data must seem like a potential solution. They face significant limitations that require broad training on all possible workload behaviors, and they must be trained for every possible hardware configurations. This makes them sometimes somehow impractical for real-world deployment. And, and instead, online reinforcement learning offers a more practical approach. Our agent can learn from interactions with the environment and adapting to new patterns without requiring pre-training. Let me walk you through our solution, ArtMem. We will introduce the adaptive migration in tiered memory. And here is the overall architecture of ArtMem, our best tiered memory system. Our system has three main layers. At the top, we have our own framework that makes intelligent decisions about page migration. This includes a Q table that learn optimal actions for different states and a reward system that provides feedback on migration decisions. In the middle, we have the software layer for ArtMem that process distributions information, perform page sorting, and adapts to threshold and migration volumes based on our decisions from top layer. And at the bottom, we have the hardware layer that includes fast and slow memory tier, plus PMU support for efficient access tracking. And here, it's important to know that we need to combine all these layers to make dynamic and adaptive migration with low overhead. And let me explain our framework design. ArtMem employs a Q learning-based model in reinforcement learning approach. We quantize the DRAM access ratio into 12 discrete states. This gives us a compact representation that captures how well the system is currently performing. And we use two separate Q tables to control key migration parameters, one for frequency-based threshold, hotness threshold, and another for recency-based migration numbers. Our reward function and balance two objectives in improving the fast memory access ratio while penalizing unnecessary migrations. This design keeps the state and action space small enough for efficient queue table updates, while still capturing the necessary decisions needed for the effective migration. And once the RL agent selects actions, ArtMem enforces these decisions through several mechanisms. We track page access patterns, use exponential moving average to capture the distribution typically seen in memory access. And we use LRU-based page list to incorporate recency information. Importantly, we adopt a greedy policy where migrated pages are always placed at the head of the active list in the destination tier. This ensures that recently accessed pages get proper priority. The system dynamically adjust both the hotness and the migration number parameters based on our decisions, allowing fine-grained control over migration behaviors. And to integrate reinforcement learning without impacting application performance, we use lightweight background threads to do this option to do migrations. We use process event-based sampling to periodically collect memory access events. And this provides the environmental feedback needed by our agent. And the migration threads perform page movements between tiers based on the current RL selected in migration parameters. And the design ensures that our learning and migration operations don't interfere with application execution, maintaining low overhead. And here's how everything works together in practice. We initialize Q table and migration parameters. We're giving high Q value to the no migration when DRAM access is 100%. Background thread will collect data, and then we update the Q tables and reverse and execute the selected actions. Then we updated the EMA and RIO list and performing actual page migration. This process repeat continuously with our agent learning and adapting to changing access patterns. And now let me show how well ArtMem perform in our evaluation. We use DRAM as the fast memory tier, and we use Intel persistent memory as the slow tier. We compare against 7 state-of-the-art tiered memory system, and we run this. We use 8 representative memory-intensive applications spanning database, graph processing, HPC, and machine learning, and more. We test 6 different DRAM to PM to persistent memory ratios to evaluate performance across different scenarios. And this is our main performance result. The graph shows execution time normalized to ArtMem at 1:16 ratio, so lower is better. ArtMem achieves remarkable performance across different memory ratios. It performs best or second best across all cases. Most importantly, ArtMem achieves an average improvement of 10 to 44% compared to the best baseline for each workload, and shows better adaptability compared to other SOTA systems. And let me dive deeper into why ArtMem works so well using SSSP as a case study. SSSP has a broad distribution of hot regions with minor difference in access frequency between these hot and cold areas. This makes it challenging for traditional heuristic-based methods to identify the right page to migrate. And the IO-based is more proactive in selecting operations that maximize the rewards. As you can see in the right figure, ArtMem consistently achieves higher DRAM access ratio across all these memory settings compared to the heuristic-based method. This directly translates to better performance because more memory access hit in fast memory tier is strongly correlates with the overall performance, as we showed earlier. And here is another compelling example showing ArtMem's adaptive behavior with a mixed workload. ArtMem performs some exploration at the end, then achieves better performance. But interest TPP achieves a good access ratio at the beginning, but continuous migration pages. And it has 17.5 times page migration than ArtMem. And this demonstrates ArtMem's ability to learn when not to migrate, which is just as important as learning when to migrate. We also test ArtMem's robustness under different conditions. And this result, we test the memory size, different memory size, sensitivity to different memory latency, and mixed workloads. All these results confirm that ArtMem benefits are robust across different memory configurations and the memory access pattern characteristics. Let me conclude our main contribution and impact. In summary, existing tiered memory system lacks dynamic adjustment of migration parameters, resulting in suboptimal performance across diverse workloads. ArtMem addresses this through three key contributions. ArtMem represents a fundamental shift from static or heuristic approach to adopting learning-based memory management. Thank you for your attention. I'm happy to take questions.